Hello, welcome. In this short video, uh, let us look at the characterization of the LTI system using the Z transform. Specifically, we will look at two problems that can be solved based on the knowledge of the Z transforms related to discrete time, a linear time invariant system. So we are going to look at the system function of a discrete LTI, that is linear time invariant system. It is given the input x of n, the signal x of n goes through a LTI system which has impulse response h of n and the output is y of n. So the relation between the output and the input is given by the linear convolution, that is x of n convolution with x of n convolution with h of n, or h of n convolution with x of n. So the formula for this one is y of n is a summation k is equal to minus infinity to plus infinity x of k h of n minus k. So that is the output. Now in this video our goal is to look at the Z transform of the output y of z, that is y of z is the Z transform of the output, that is n is equal to minus infinity to plus infinity y of n z power minus n. And now the relation between the Z transform of the output and that of the input is given by y of z is equal to h of z into x of z. This is based on the convolution property of the Z transform. So this is based on the convolution property of the Z transform, that is y of z is equal to h of z into x of z, that is convolution in time domain is equivalent to multiplication in Z domain. Now h of z is the Z transform of the unit impulse response or the impulse response of the system. It is summation n equal to minus infinity to infinity h of n z power minus. And of course x of z is the Z transform of the input. Now this h of z is called the system function or the transfer function. Now we can solve two important problems based on the knowledge given. That is, for example, we can find the output y of n using this knowledge of the Z transforms based on, you can find the output y of n given the input x of n and the system's impulse response, that is h of n. Given x of n and h of n, we can easily find y of n by using the Z transform. That is, the first step is find the Z transforms, that is Z transforms of x of n and h of n, x of n and h of n. That means first find x of z, that is the Z transform of x of n, and also find h of z, that is the system transfer function or the system function based on the Z transform of h of n. And then the second step, that is in the second step we just multiply these two, that is we get y of z as the product of h of z and x of z. So that means we multiply them in the Z domain. Y of z is h of z into x of z. So the first step is transformation from time domain to Z domain. Second one, we do the operation in Z domain. And in the third step, we find y of n as the inverse Z transform of y of z. That is, we come back to time domain from the Z domain by applying inverse Z transform. So thus we can find the output sequence without actually doing the convolution time domain. We can just apply Z transforms, find the Z transforms x of z and h of z, multiply them to get y of z, which is the Z transform of the output, and then apply inverse Z transform to get the output sequence. So that is the algorithm. Now we also look at an algorithm where we can find the system function of the of a linear time invariant system. Find the system function, and you can find the system function and the corresponding unit impulse response given the input x of n and output y of n. That is, given the input and output of a system, we can basically identify the system, that is we can find both its system function and the corresponding unit impulse response. So here is the algorithm. So given x of n and y of n, first we apply Z transforms. That is, we find x of z as a Z transform of the input x of n, that is n is equal to minus infinity to plus infinity, and y of z, that is the output z transform, again as a z transform of the sequence y of n. So once we have both x of z and y of z, we can easily find h of z as their ratio, that is h of z is basically equal to y of z upon x of z. So this is basically conversion from time domain to z domain, and then in the second step we find the ratios of the z transforms to find the system function h of z, and in the third step we apply inverse z transform, that is to find the impulse response of the system. H of n is the inverse z transform of h of z. So basically we come back to time domain from the z domain, that is we can find both the system function and the corresponding time domain unit impulse response from the given input and output, for of course for a linear time invariant system. So basically the idea is that h of n and h of z, which basically form the z transform pair, are describing the same system, one in time domain, other one in z domain. So to summarize, we have looked at the important properties, or at least two applications of the system function of a discrete LTI system, that is given the it can be described by a simple relation between the input and output, where y of n is the convolution of the input with the system's unit impulse response. It is basically given by the convolution formula. The output y of n is basically given by convolution between the input and the system impulse response. And then we looked at the z transforms of the corresponding signals, and h of z is basically the system function. It is also the z transform of the impulse response. Now we look at two algorithms. The first one is we have to find the output y of n given the input and the system impulse response. So the algorithm is as follows. First, find the z transforms of the input and the impulse response, that is x of z and h of z, and then the second step we multiply them to find y of z, and in the final step y of n is the inverse z transform of y of z. That is, we can find the output sequence based on the input and the impulse response signals or sequences. And in the second algorithm, we find the system function or identify the system and corresponding unit impulse response given the input and output sequences. The first step is we have to find the z transforms of the input and the output respectively. And in the second step, we find their ratio, that is we find h of z as y of z by x of z. And in the third step, we find h of n, that is the impulse response, as the inverse z transform of the system function h of z. So basically, both the impulse response and the h of z are describing the same system, one in time domain, other one in z domain. Thanks for watching.